the neuromorphic or the semiconductor, right? Today I talked to another student, we were saying, oh, it was very amazing. Nowadays, even if we see COVID-19, the electronics is the one that is still growing, right? 20 years ago, the visiting scholar in my school told me that you should quit semiconductor. This is the end already. What is a STT RAM? This is the figure that I want to show you. Now I have the drawing. You see it becomes more complicated. The free layer has two stable states, right? With reference to the reference layer. Now you see that, do you see that now? You have more layer. I have the MgO. This is the insulator, what I told you earlier. Okay, and this is the free layer. The whole thing at the bottom is the reference layer. Why it makes it so complicated? Because they want to stabilize the reference layer. Okay, we won't go into the details, right? But first of all, reference layer is changed by referring to the, free layer is changed by referring to the reference layer. So they align in the same direction or opposite. That is how we store the information. Okay, and how do we stabilize the reference layer? Reference layer need to always be referenced, right? If it got flipped, then we get the wrong information. So what we do? We will use so-called antiferromagnetic exchange coupling, right? Ignore this. You may see this in the literature, but the main point is you see that we have magnetic sublayer, ruthenium, magnetic sublayer. The whole thing become a so-called synthetic. They are not really antiferromagnetic. Like this one, you have two different lattice. But you see, we try to make them in different direction. The overall effect is just like they are antiferromagnetic. Okay, but we call it synthetic antiferromagnetic because you make it, and they are actually ferromagnetic, but you make it like this. Okay, but no worry about this. You can ignore now. You just need to know that reference layer is not that simple. It's not one layer or not even 4 layers. It is 10 or even more. Try to find a real paper. You will see that. Okay. And what is the common magnetic material? Cobalt, iron, boron. This is a magnetic material. People find it to be useful. So what I'm saying here is that these are cobalt, iron, boron, cobalt, iron, boron. Most of them, right? For complicated one, you will see other stuff. And then the insulator is magnesium oxide. This is very important because it's going to determine the selectivity of the spin. We'll discuss later. It's going to affect your reading ability. Okay, so in summary, in this slide, I only want you to have the concept that, first of all, STT RAM is not simple, not just 3 layers, but it has 3 functional layers. One is free layer, one is the tunneling barrier, one is the reference layer. But the reference layer can be very complicated. For example, it can be a multi-layer to have the synthetic antiferromagnetism. This is one thing. Second thing is, if you can memorize, I'm not asking you to do it in the exam, but you know that tunneling is magnesium oxide, cobalt, iron, boron are the magnetic. Okay, and then the third thing is that you can make the polarization laterally or make it vertical, right? It's up to you, right? You can align the magnet north-south laterally or vertical. So this is called in-plane design, IP. This is called parallel plane design. Parallel. I think I'm correct. P stands for parallel. Okay. No, I'm wrong. This is perpendicular, right? Perpendicular. Okay, because it's vertical, right? I tell you PP is better. Can someone guess why PP is preferred nowadays? I think it's difficult for you to know that. For the main point is that when you make your magnet smaller and smaller, the magnetization is less stable. It is also pretty intuitive, right? If I have a lot of like a bulb, then they will be stable. If I make it small, I have a lot of edge effect. If I try to make this very, very small, you can feel that, right? Maybe you don't know, but I can tell you, anisotropy is very important in the stability. So if I make it very elongated, then this one will be pretty stable, right? Think about this is so thin, then it will prefer to polarize horizontally. But that is not good because it means that my cell density will be low. I need to keep this one very, very wide. If you are used perpendicular, it basically does not depend on how wide it is. You only care about how thick it is and other stuff. So I can make this really small, right? Basically, I'm going to erase this, but what I'm trying to state is that you just a drawing, you feel that if I make it so small, you have a feeling that, no, this one might not work anymore. But if I make this so small, you will say, looks like it's okay because the whole arrow is still contained inside, right? So perpendicular plane is promising for the future scaling. Again, this so-called low-flow memory is attractive. One of the main things is they're simple. We can use the crossbar structure. Remember the crossbar we talked about for writing resistive memory? It's the same here. So we want to make it small. If it cannot be made small, it's not competitive. Any questions? Now, still just a basic, right? But that's it, right? Now, what else can I tell you? I'm going to tell you why the reading currents is going to depend on whether your reference layer is align or opposite to whether the free layer magnetization is align or opposite to the reference layer, right? So, but before that, we are not going to derive the equation, but as I tell you, they are the same. So there are some characteristics that as I tell you, they are important. That there's some characteristic we need to know about the STT RAM. The first thing is the thermal stability. So how do we find the stability? It's just very simple, just EB over KT over KT. What is EB? EB is just the energy barrier. Cool. Flip the magnetization. Right? Remember I say that you have a free layer. You might be pointing in this direction. This might be my reference layer, right? Well, if it is hot, maybe it suddenly flip my bit to here. That will be bad, right? Originally, let's say they are aligned, it is 0. And now they are opposite. Then it becomes 1. But how can I flip it? I flip it need energy, right? And this is the flipping energy barrier. Well, if it is large, that is good. But what we care is how it compares to the temperature. KT, of course, is the thermal energy. If you are at a higher temperature, you have higher thermal energy. You get flipped easily, right? For example, at remember what is the thermal energy at room temperature? Anyone?
300.
300 is the temperature, but what is the thermal energy? Of course, you can plug in 300 T times the KB, right? Boltzmann constant. Say again.
Thermal energy, you mean it's in terms of, yeah, thermal energy. Do you mean thermal voltage?
You can say thermal voltage.
Okay, so it's around 26 milli EVs.
Wonderful. If you give me 26 millivolt, that is thermal voltage we use in BJT, right? And very good, you convert it to the milli EV. Milli EV is the energy for one electron to travel across the thermal voltage, right? So 26 milli EV. Okay, so if you want it to work in the room temperature, you definitely cannot have only 26 milli EV of energy barrier. Then a lot of them is going to be free. I don't know how many, maybe 10, depends on your requirement. Then maybe you get flipping for every second or every 1 day, one flipping for 1 gigabit of memory. Okay, so this is thermal stability, and this is the only thing we're going to learn about thermal stability, but this is very important. Another is the so-called tunneling magnetic ratio. Okay, magnetoresistance ratio, right? TMR, which I mentioned here. Tunneling magnetoresistance ratio. Basically is that now I actually been using not a very appropriate word for this. I keep saying a 9. I should actually correct myself now. Right, let me go back to here. I keep saying a line. What I mean is parallel. You are in the same direction, right? This is a more professional word. An anti-parallel. Okay? AP. I hope you understand what I mean, right? They are pointing in different direction. Same for here. This is a parallel, anti-parallel. Right? AP. So when you read it, the resistance is different. It's equal to the anti-parallel resistance minus the parallel resistance divided by the parallel resistance. For example, if your state is anti-parallel, you may get, let's say, I don't know the real number, 10 kilo ohm, let's say. If it is parallel, it may be only 5 kilo ohm. 5 kilo ohm. What is this? This is 100%. This is a pretty good TMR already. You see that it's not usually what we think on off, that you have 10 to the power 1 million times of difference in the current. The resistance is only 100% difference. This is in the right order. Other people start pushing more, 200% or more, but I never see something that is 10 times. Okay, this is very subtle, right? So anti-parallel is talking about when what I try to measure, R is this. You have this one, you measure the current, you apply a voltage, and then R equal to V divided by I. That's what we mean by R. Is this okay? This is the resistance of the resistive of the STT RAM. So when it is parallel, it has lower resistance than when it is anti-parallel. And that is how we distinguish whether it's at 0 or 1. Right? So this is about reading, right? How you read the content of the STT RAM. And then another characteristic is about write. How can you program it so that it flip the charge, right? Even you have a very good memory, but I need to use very high currents to flip it. I don't want it because it's consume a lot of power. So 3 characteristics: particularly important for STT RAM, stability, right? You just find the ratio between the flipping energy and the thermal energy. Thermal energy like the thermal voltage. The tunneling magnetoresistor ratio, what's the ratio between parallel and anti-parallel, right? Which I did not name it well at the beginning. I call it align and opposite, but we should call it parallel and anti-parallel. Right? But if you say align opposite, people understand also. But I think they will think that you are not that in this field. And then what is the current required to flip, right? How do we write it? We're also, again, apply a high bias to it, right? So that it can flip. That means maybe, right, I have this one, and then apply a critical current when I want to flip it. Let's say IC, then it becomes something like this after a certain time. So you change from anti-parallel to parallel. You change from 0 to 1. Okay, that's how it works. Any questions? Now, if no, then now I think you know how it works already, right? And all the figures of merit, right? So if you are a circuit designer, you are done. You can leave this class now, right? For circuit designer, this is what you need to know, the stability and everything, right? But we want to know more about the physics. So here I want to emphasize something is very confusing to many people. For every atom, we have inner shell, and that is responsible for magnetization. Okay, so how to draw it? Let's say you have an atom here, right? And you have this inner shell, okay, 2, 2, and then maybe 8, right? They are going to have the so-called magnetization. For example, they're pointing up. So when we say the free layer is polarized in certain direction, it means this at all the atom are pointing, all the electron of the inner shell of this atom are pointing in certain direction. That is what we mean by magnetization. Right? Electron spin, I'm talking about electron spin pointing in certain direction. And there's still another type of atom, which is the extra electron, the conduction electron. Right? It can point up or point down, depends on what it is. These are the electron that's transporting. Remember, when we talk about all this semiconductor doping, right? Remember, we have the conduction band. And then there are some electron running on the conduction band. What's the valence band? Valence band are all those pi electron. They are bound to the nucleus, right? But they still have spin, right? So when we look at a material, we say this is magnetized. We're talking about this inner shell electron. They are not moving. They're responsible for magnetization. We say it is pointing north. We're talking about these electrons pointing north, right? But at the same time, we also have the conduction electron moving around. And how are they pointing determines something called spin current. Now I don't only look at the electron. I only recognize that this electron can be spinning in different direction. But for a regular resistor, if you give me, I know there are lots of electrons, any metal, but all these electrons moving, they are pointing in different direction. So basically, I have two spin current. One is spin up, one is spin down, but they cancel out each other. They either up and down. So this is the first thing I need you to understand. Is that okay? Any question on this? The picture that I have inner shell and also outer shell.
What do you mean that the spin currents cancel each other out?
Spin current is talking about the conduction electron. So I have many electrons traveling, right? These electrons are traveling from negative terminal to positive terminal. These are the conduction electron, right? In any resistor. Is this okay?
Yeah. Are you saying that total spin is 0?
Yes. And then why I might have them spinning in different direction, right? So they cancel out. Is that okay? What I'm trying to tell you is that these electrons that are moving, they have spin also.
Okay, got it.
Okay, good. Right? So this is the picture I really want you to memorize, because many people don't recognize it. If you don't recognize this when you start reading paper, you cannot understand. You have to recognize in the free layer, right? Magnetization are responsible for this inner shell electron. They are not moving. They spin up, spin down, but they are not moving. However, there are some electron moving around, the conduction electron. They can spin up or spin down. Okay, this is the picture. So if this is clear, I'm going to tell you another concept called polyparamagnetism. So what does it mean? This is about the inner shell electron. If you try to look at the energy of the electron, you actually have two types. It can spin up or spin down, right? This is the density of state. So now I just try to group, right? We call it boy and girl, not that good right now. They try to avoid any of this, but I think this is equal here. We can call it boy and girl, right? We are all human in the class. And we have boy and girl, or spin up and spin down, right? And then when you go up with the energy, when it's higher, the density of state will be different. But before you try to distinguish them, they are all filled up to Fermi level, right? Because I don't have any magnetic field. Spinning up or spinning down is the same. They all fill up to Fermi level, right? If there's no magnetic field, can you distinguish whether it's spinning up or spinning down? Probably not, right? Okay. Now, what if I apply external magnetic field? Let's say I apply a magnetic field that is pointing upward. What will happen to them? Then there will be an interaction. Extra energy will be equals to negative magnetic moment dot the magnetic field, right? I don't need you to memorize this, but basically it is saying that if you align, or how about let's call it parallel will be better, parallel with B, the magnetic moment, parallel with B, you have lower energy, right? Because you're in the same direction, you get lower energy. But this is the magnetic moment. Of the electron, okay? So, but magnetic moment is opposite to spin direction in electron. Okay? This is given, right? Either you study it before or I just tell you it is opposite. So it means that, right, I would like to have the spin in the opposite direction of the magnetic field. So let me draw it, then you know what I'm trying to say. This is the energy when you have the external magnetic field. Because of this extra magnetic moment, mu dot B, okay? Because of this. The one that is opposite to the magnetic field actually get more field up because it has lower energy. And the one that is in the same direction of the magnetic field actually get less. So because of this external magnetic field, I have more spin down than spin up electron. This is what we call polyparamagnetism, which tells us that overall, because this is spin, it means magnetic moment is going up. The whole effect is that I have a paramagnetism. I try to align with the magnetic field. Right? I don't know if you can follow me. You can try to replay many times when you go home. But the main concept here is this. You need to recognize that the inner shell, we're talking about inner shell electron, they can spin up and spin down. When there's no magnetic field, we literally cannot distinguish which one has higher energy, right? It's just like you say you have negative and positive charge. If you don't apply electric field, they have the same energy. So as a result, they all fill up to the Fermi level and they have the same energy profile. If I apply external magnetic field, it actually will make me to have more electron in the opposite direction of the magnetic field because they have lower energy. And I give you all this equation. It's good to learn. I don't expect you to learn. But you do need to know that under external magnetic field, I will get more electrons spinning in the opposite direction of the magnetic field. This is important. It's just like saying that originally you have, let's say, half of the magnetic field spinning up and down. After I apply the magnetic field, I may get this. I get more electrons spinning down. This is like the polyparamagnetism. Any questions? Right, so this is the picture, right? Remember, now in any material, you have atom, then you have electron, and you have some electron bound to there, we call inner shell. Their spinning direction responsible for the magnetism. And they also obey this polyparamagnetism. Originally, they spin in different direction, but now you apply external magnetic field, most of them will pointing in the opposite direction. And don't forget, we also have some naughty kids running around, the conduction electron. And they keep running around, but they still carry the spin. They still pointing somewhere. But we don't care usually because they can be up and down. Okay? Then what happened? What do I want to say? This is what happened. When we are in the parallel state, this is the free layer. This is the reference layer. Because they have the same magnetization. Remember, what is this? This is the inner shell, right? They all pointing to the left due to the inner shell, right? So the inner shell, they form the polarization. So this just like the external magnetic field, right? It's just like the external magnetic field. So because they're pointing in the same direction, isn't that for the free layer, this is the free layer, and the reference layer, they all have the same direction, getting more electron. Actually, I'm sorry. I think I say something wrong. This is not for inner shell, okay? This we're talking about, because we're talking about this density of state, that is actually the conduction electron. This should be the conduction electron. We're talking about how the conduction electron distributes, right? So at the beginning, they all pointing in two directions, so they all cancel out the spin current, right? If I apply external electric field, some of them will prefer pointing down. And this magnetic field can come from the inner shell, okay? Sorry for confusing you. Is this clear or no? Right, but anyway, the point is the inner shell is just like external magnetic field. They're pointing in the same direction, so I split them into two layers, right? The free layer still have less pointing down and more pointing up. The reference layer also has less pointing up and more pointing. It really depends how you write it. Pointing up, this is down, sorry, yeah. If they are anti-parallel, what will happen? Then maybe the free layer has more pointing up, but the reference layer has less pointing up. Then what does it mean? Then if you want to have tunneling, you need to have the tunnel in the same direction. Pointing down need to tunnel to pointing down. Pointing up need to tunnel to pointing up. And because of this, now you see that if they are parallel, I have a lot of electron here to tunnel to here. So I have large current. But this anti-parallel state pointing up can only tunnel to a very small density of state. But pointing down can tunnel to a lot of spaces, but you only have very few sources. That's why you have a poor resistance. Okay, maybe I stop here and we'll continue next time. Okay, let me know if you have any questions.